Hello everyone! In this video we will continue to examine topic 5.2, the heating effect of electric currents. And in particular, we are going to return to Kirchoff's second law. Okay, so hopefully at this point you've had a chance to work through many of the complex combination of resistor problems that are given in the notes. Okay, and I'd strongly recommend that you do so before moving on. We're going to return to Kirchoff's second law. As I mentioned when we first introduced it, Kirchoff's second law is actually quite powerful and can be a little bit complex when applying it to sort of more complex circuits. And Kirchoff's second law will allow us to analyze circuits that, using the rules we have, are actually impossible to analyze with what we already know. And just to give you a little bit of a sort of an advance on what this is going to look like, in a little bit, once we figure this out, we'll figure out how to deal with circuits which involve multiple batteries, multiple resistors, wired in sort of different or unexpected ways, as you'll see here. But before we get there, we need to sort of revisit how to apply Kirchoff's second law to complex circuits. So when I first introduced this, I basically said, all right, draw a loop, and then you go up the EMFs and down the resistors. This is generally true, particularly for simple circuits of the kind we've already dealt with. But it's important to recognize that to really use Kirchoff's second law, you need to be prepared to A, not know what direction the current is going through the resistor in, and B, to be able to deal with sort of multiple pathways. So we're going to detail this process a little more specifically. The first thing you're going to do is draw the circuit diagram, label it with known quantities. In this case, EMF1, EMF2, and 2 resistors. Then you're going to make an educated guess as to the direction of the current in each branch and label it. If you get it wrong, the algebra will take care of it for you because the current will turn out to be negative. But you always want to label the current. In this simple circuit here, the current is labeled as going in this direction. You will then want to draw a loop to analyze with a direction. So notice I could have drawn a different loop, and in some circumstances I will. We'll deal with that in a bit. But for now, I'm going to draw a loop. Notice that my drawn loop does not have to be in the direction of the current. I will tend to do so just by default. It's nice to have a convention. But if you don't know the direction of the current, sometimes you just got to go with your gut and draw the loop, however you'd like. But you need to be prepared for the fact that your loop direction might be a different direction than the current. So in the loop, then you want to add up all the potential difference gains and drops. And the key thing to recognize here is that a potential difference gain may include a battery, but it also may include sort of, quote unquote, going the wrong way through a resistor. In particular, if your loop direction faces against the direction of the current, you are increasing your potential difference. And so it's important to sort of keep track of all types of potential difference gains, not just EMFs. Similarly, if your loop direction drops through an EMF, it's going the opposite direction of the battery, then that counts as a potential difference drop and not a potential difference gain. So consider, for example, delta V and the loop in the same direction. This is what we have done so far, basically, right? That means the current will be going this way out of the battery, and our loop direction is in the same direction. This means that this is a gain from V low to V high. As a result, delta V is positive. So we're going to use positive EMF for that situation. What happens if the current is going from V high to V low? So as in this case, this is, again, our standard case. The loop direction is in the same direction as the current, and delta V is then negative IR. Remember, this is subtracting your potential drops. That's what's going on here. It's a drop. You're going from V high to V low through the resistor. Now what happens if they're in opposite directions? Well, consider this for a second. If you are going from V low to V high, and the current is going this way, but your loop direction is going in the opposite way, then you want to keep track of that as a potential drop, equal to negative the EMF of the battery. Okay? Negative the EMF of the battery. And likewise, if the current is going this way, from V high to V low, but your loop direction is going the opposite direction, then that will count as a potential gain rather than a potential loss. So now apply Kirchoff's second law to this circuit up here, okay? Well, if this is our loop direction, then in our initial analysis, we would say, okay, we go up EMF 2 and up EMF 1. Therefore, the sum is EMF 1 plus EMF 2. And then we go down the first resistor and down the second. And so we add those potential drops, so to speak. And so that's negative IR1, so minus IR1 minus IR2, where IR1 is the potential drop, okay? And this is key. So this kind of substitution, where we're multiplying that current by the resistance, we will substitute in part because it helps us keep track that those are potential drops through the loop, and in part because we're going to end up using this as an equation later on. So notice we're substituting for the definition of resistance when we apply this. Then you can solve it out, and you get that EMF1 plus EMF2 equals I times R1 plus R2, which is sort of what you would expect given our initial analysis. Okay, so this hopefully is not terribly surprising. So what if the loop that you drew in here, instead of that pink loop, was a purple loop going the other direction, right? How would that affect your analysis? Well, due to the reverse in the loop direction, you'd pick up a minus sign on every term. So this would be minus EMF1 minus EMF2 plus IR1 plus IR2. So going down this potential drop, down this potential drop, right? So down the escalators, so to speak, and then back up and back up here is plus IR1 plus IR2. Notice you get the same equation, which it should not be surprising. This is the same circuit, so your analysis should not depend on the order in which you do it. So now, in the next couple of videos, we're going to take this Kirchoff's second law tool and apply it to some more complex circuits.